Thank you very much for the opportunity to speak here, for the invitation, for organizers for this wonderful workshop. I'm going to talk about projection theorems and applications. I know this topic is a little away from other topics in this workshop, so please feel free to stop and ask any questions. So, suppose that V is a k-dimensional subspace in Rn. So we define PV as the orthogonal projection of Rn to V. So the question that we are interested in is, suppose we have a subset of Rne, and lambda is a subset of the Grassmannian, a set of k-dimensional subspaces of Rn, and they are both compact. The question is, what is the supremum of the Hausdorff dimension of the orthogonal projection image of E for V in a set of k-dimensional subsets? So we are interested in so this is the question that we are interested in, that what projection theorems studies. Well, the answer is the answer depends on E and lambda. For example, one can think of one enemy example is you take okay, maybe I should first say it's a simple example when k is 1, and then so V is like a line, so it's say spanned by theta in a unit vector theta. Then we can also say P sub theta n to R defined by, so X maps to the dot product of X and theta. So for most of the talk, we're only interested in this dot product, this orthogonal projection. And for example, one enemy example for this question, when k equals to 1, is we can take suppose that this lambda is this great circle, and then we take our E to be a subset of the line of a line L that's normal to this great the hyperplane that contains this great circle. And in this picture, so this is our E. In this picture, we know that for any theta P theta of E is just because they are orthogonal. And so this is an enemy example that if we want a good estimate of such group, we want to avoid it. But before that, there is the classical theorem of Mastro and also by Martina. So Mastro proved low dimension version and Martina say that. So their theorem is about, say, this lambda is the whole set of the Grassmannian for almost every V for almost every k-dimensional subspace. And the constant dimension the projection image equals to the minimum of the positive dimension of E and K. So roughly speaking, for almost all projection, we keep the dimension or it reaches the maximum dimension possible. Now, because here we have access to almost every case subspace, so we can here is like in this case we have access to almost every directions. So this is not almost every, and that's one way to get rid of this enemy example. But in some cases, we don't have access to almost every case subspace. So what can we do? So there is this, for example, one question that I learned that might appear in dynamics is we are interested in this kind of projections. X1 x2 x1 plus b squared x2 plus to the n xn. Well, sometimes you divide by t, but essentially it's this map. So one that is interested in knowing, like, under this map, how does what's the dimension of the projection image by t of E? And so this question was also asked by so this was first one Orponen. I think in 2013, they asked a question of this type. So suppose that the set of directions now it's like the direction is t squared. So in this picture, this will look like if we divide by the norm of the vector, it will look like this one. That's like lambda. When our new lambda is here, it's no longer a great circle. So this enemy will not exist. And this is like a quantitative way of saying that it's not a great circle. So for most of this talk, we'll be talking about these projections. This projection. Are there any questions so far?
Yeah. Well, what was the result by Kassler or Orponen?
They asked the question.
Oh, they asked the question. Okay.
And then I will say what's they also show some result. I will say what's the result is. This is the result. I write it beforehand because there are many names, just in case, so that I don't forget. Also, this is not a complete list of names. So this is the result. Say let gamma from 0 to 1 to Rn be a non-degenerate curve, meaning that the determinant of gamma prime and gamma n to the n is non-zero. Let E be a compact subset of Rn. Then for almost every t in 0, 1, and this V, K, T means this, like the span of the first K derivative, like some sort of K tangent plane of this non-degenerate curve at point T. The conclusion is that the Hausdorff dimension of the projection image on this K-dimensional subspace equals to the minimum of the dimension Hausdorff dimension E and K. So we obtain like a Mastrong type theorem with only the directions on this non-degenerate curve. instead of the whole cross management. Yeah, that's the result. And so when D equals to 3 and K equals to 1, this can argue Orponen and they proved for a special curve that's like the lambda, the red lambda up there. They proved for this curve, and later by Pragmatic, Yang and Zhao, they proved for general non-degenerate curve. Then also by Gan, Guth and Maldague, they also proved for a general non-degenerate curve by using different methods. So I should say that this group and this group, they use a method developed by Wolf and Schlag. Curve calculus. So it means that intersection of some C2 curves in R2, some neighborhood of C2 curves. So they use this method, and this group, and later when D equals to 3, K equals to 2, and there is another group that's like this is so all the rest uses a Fourier analysis method that we are going to discuss next. So so with Gan and Guo, we proved the general cases for all D and K, K smaller or equal than D. So this is the thing that we are going to talk about.
So you said they proved for that red curve?
Yes, so I think the set is 1 cosine theta sine of S2. So this is the set.
But does that satisfy that determinant being non-zero condition?
So yes, that's a good question. So it is. So this is. So here we are when K equals to 1. This is the span of gamma prime, and the direction is gamma prime. And this curve, what I mean is like this gamma prime. So there is one derivative.
But you need the determinant being non-zero there for 3 derivatives, or?
So I think in reality, if so this corresponds to a curve whose gamma prime theta is that. And then you take the double prime and triple prime, the derivative will be.
Thank you.
So so you can also formulate as gamma and gamma to the n-1, and now here you want to map it to say as n-1. It's equivalent. Okay. So for the rest of the talk, we'll be focused on K equals to 1, and then also we will discuss general method that's that can probably we'll discuss its connection to Fourier analysis and decoupling theory, and also say in the end say something about where this method works well and when it doesn't. Okay. So before that, I want to introduce a notion, say a notion of delta T set. Say delta positive is, so this delta T set is approximation of a T-dimensional set. Well, so this delta is the scale, and we should think that it's very close to 0. So a delta T set E is union of delta balls satisfying This notation, say, so we call this delta covering number means the minimum number of delta balls needed to cover E. So this sometimes we call it a ball condition, means that the set, the unit of delta balls are not concentrated in any ball. So
Should the exponent of R be T, not delta?
yeah, that's good. Thank you, Kevin. Yes. So this R to the T means like how non-concentrated it is. So the T is dimension. When the dimension is smaller, should be sparse. So one thing, one easy consequence of this definition is like from a delta, if E is a delta T set, then the delta covering number of E is greater than delta to the minus T, because we can take R to be delta and then P delta to be one delta ball E. So the left hand side is 1. And then when R is delta, so we move this to the left hand side. It shows that the delta covering number of E is at least delta to the minus T, but it might be a lot larger. So
I have a question. Can you give an example of something that wouldn't have this property? Or is it?
So you mean wouldn't have this property for any T? If T.
Or maybe for a fixed T?
Okay, sure. Yes. So if you have, say, if your set E is a line, then you take a T equals to 2, then E is not a delta 2 set.
Oh, okay.
That's a good question. So I think this should be used as a definition for set of dimension at least T at scale delta, not exactly T.
Okay.
Then so when we study this okay, so now the setting is suppose delta T set. Then lambda, since we are considering only k equals to 1, delta S set. So here we want to assume that T is less than. And then for each theta lambda, so P theta will map, let's say this direction is theta. Then we have a set of delta balls, that's our E. And so this P theta will map E to this line. And we consider those fibers. So each fiber will be like a delta neighborhood, because everything is at scale delta, a delta neighborhood of n-1 plane of a hyperplane. So here, let me just say that we can assume E to be in the unit ball to make things. And the P theta is the map. And then, so that's T theta be a set of 1 times 1 we call them slab T theta. And that's normal orthogonal to the theta direction because it's a bipolar. And so in particular, the slabs in the collection T theta is they are parallel because and covers whose union covers. So intuitively, if the projection image is small, then we can find a small set of slabs that covers E. And then that slabs. So the method is we're going to study the incidences between this T and E and conclude that for most of the theta, the set of slabs that covers E cannot be too small, and this will prove a lower bound of the projection image. Okay. Oh, sorry, I just forgot to mention applications. Sorry, there are two applications about this theorem that I know so far. One is in dynamics. That's the work of Strauss, Mohammadi, and Wang, who is not me but sitting here, they proved that they proved some effective equidistribution results using one of the tools is to use this result about restricted projections from R3 to 1 to 1R. So from my understanding about talking to people in dynamics is that, which is very limited, is that so we don't like when the orbits are equidistributed on some low dimensional thing, and this low dimensional thing will maybe I should make it red. So this low dimensional thing will somehow lift to that red lambda, and if it's equidistributed on the whole thing, then it's kind of like we have access to every theta on the sphere. That's my understanding. I'm not sure that that's correct. So that's why such kind of projection theorems can be useful. And the other application is like some special cases of Kakeya problem. I will not say too much about that. Okay. I hope that gives the name applications, and then I will continue to the proof.
Sorry, can you say in the application to Kakeya, is it cases where you prove Kakeya under some extra assumption?
Yes, so there are special cases.
So can you just say a word, since it does sound very interesting?
Yes, so the one case is like say the Kakeya set is a set contains a unit line segment in every direction. So if we impose the condition that lines that are parameterized by in the parameter space is parameterized by points in S, L to Z, and then you can say that those Kakeya set has 4 dimensions. This was the result by Castro and Orponen. Also, by Katz, and Zhao. Well, they use this Wolf-Schlag circular Kakea method, and they also managed to reprove this result. So this is for the so-called SL2 Kakea set. Another special case is about.
This is in 3 dimensions?
Yes, so in 3 dimensions. Another special case is about sticky Kakea sets. So when the lines in the Kakea set are as close by as possible, like sets in lines in nearby directions stay close, and it's by this joint work with Zhao. We show that those sticky Kakea sets also have Hausdorff dimension 3 in R3. So the last step uses one can use the this result or of restricted projection from R3 to R. So that was the 2 special cases that I had in mind.
Thanks.
Okay, thank you for your question. So I will talk about the proof and how it's related to decoupling. So we have a collection of slabs. So the picture is in each direction we have those parallel slabs, and then in some other directions. And we also have a collection of points T, E. So and we are interested in studying the set of incidences that's the pairs X. So X now is a delta ball in E, and T is a delta slab in T, such that X intersect X. So if we manage to show that this incidence has some, so if we manage to show that the number of slabs is large, then we can show a lower bound about the set of the dimension of projections. So we are going to estimate this incidence by Fourier analysis. So let for each slab T, let phi T be a smooth bump function that's like the characteristic function of T. But we make it smooth because we are going to take the Fourier transform. And then let F be sum over phi T. And when we do integration, integrate F on E, this is like it's related to the number of incidences between E and T. So maybe up to some scaling factor, but these two are almost the same. Also, we have a lower bound that's like the volume of E. So that's the delta covering number times delta to the n, and then delta to the -1. This means that because it's lambda now, sorry, that should be the delta covering number of the set lambda. And in the case that we are interested in, the directions are supported on curve. This is delta to the -1. So we have a low bound, and so I said that we are going to study this Fourier analysis. So look at the Fourier transform of phi t. So when t is in the fraction t theta, means that this is a slab that's normal to direction phase. And now, after some calculation, this is approximately the same if we ignore the tails. Approximately the same as a constant, that's the volume of t, times the characteristic function of, I would say, delta, theta delta, which is the tube that has radius 1 and length delta to the -1, pointing in direction beta. So this is in this talk, one can just think that the Fourier transform of phi t is like this function, and then so when we think of the Fourier transform of f, it will be the union, also centered at the origin. It will be the union of those tubes. And we can see that the union of those tubes, they intersect a lot near the origin, but they are like from different directions, they are more disjoint when they are far apart. So we're going to do a decomposition of high low frequency. We take a small ball of radius that's slightly smaller than the length of each theta delta. So that's delta to the -1 plus epsilon, where epsilon is positive arbitrarily small. And the inside, we call it low frequency part. And we only, so the low frequency part is defined as a Fourier transform of f. And we called it this, that in the ball of radius delta to the -1 plus epsilon centered at the origin times smooth bump function at b, the inverse Fourier transform, and the high frequency part is like more you think that this is a function that's on the complement of b. So for the low frequency part, what it happens is when t is less than 1 here, it's not too difficult to see that the low frequency part never dominates. So at the point E, this FL can never be bigger than F. The reason I will illustrate just by picture is that what happens if we we take Fourier transform and then we do a frequency cutoff, take only the smaller frequency part. So this is like amorphous. So this function is like an average of something that's thicker than theta. So this is making this averages that's and when the dimension here, when the set E has dimension smaller than 1, so we can think of the points in E they are relatively sparse, and we are doing this average. So one can think that because things are sparser, so average usually cannot be bigger than the original thing. That's like very rough explanation of why the low frequency part doesn't dominate. But if you are interested, you can do the calculation by yourself, and it's not complicated. So we'll focus on the high frequency part. And usually in this type of method, usually the low frequency part does not cause a problem, and the high frequency part is something that we need to use many tools, and sometimes it doesn't work. So after the explanation I had, let's suppose that this is dominated by a constant times the high frequency part, and we will take absolute value. And so how to estimate the high frequency part? Here you can see that the slabs in the same collection, because they are normal, they are parallel. So when we take the Fourier transform, it was supported, those parallel slabs were supported on the same theta, because the theta tilde, because it's like the tube through the origin and pointing in direction theta. So we can define that theta sum over by t, and t is in the same direction. And then, so if we define f theta high frequency part this way, we can see that the Fourier transform of this function is supported on the outside of theta tilde. So we take off the middle part, that's low frequency part. And outside, because there are two pointing in different directions, their overlapping is very small. So this is less than the volume of E to the 1/2. And this is by Cauchy-Schwarz. And then by Planck-Schrell, we can take the Fourier transform. And since the support of the Fourier transform of those functions, they are like disjoint because they are outside. And so we have disjoint. So this is less than sum over theta. That's the definition. And so this is the key step. And that's in this method. Later we are going to see how we improve this step when certain things happen. And then we take the Fourier transform. So now because this is a frequency truncation, we can just remove the high frequency part. And since each f, so this step is the only step where we need to discuss that it's high frequency. And the last step, because then we take partial and then this Fourier transform is removed. And f theta is a sum over those parallel disjoint slabs. So this is phi t squared. And each phi t is like a characteristic function. Taking square doesn't change its value too much. So in the end, we get something like and you can, so this you can say that it gives an alternate proof of Maldague's projection. So far we didn't use anything about our set lambda and E yet. So this is a pretty general theorem and the key step is this step. One might ask, can we do something better? So let me write out what this step says. It says that, so we have, let's say G is FH, and it says that it's a theorem of this type. So this is a theorem of this type. You can also give it a name called L2 decoupling. That's the decoupling inequality that we are going to discuss.
That's real quick. I think we ended up on the wrong page. Is lambda infinite?
So we are thinking. So everything is at scalar delta. So we are taking delta separate. Yeah.
Okay, so there's some line that I should imagine on the board somewhere where it says take the original lambda and replace it with the delta separate.
Yeah.
Okay, and then I think it's makes sense.
So would there be a loss of delta to the epsilon or 1 over?
Yeah, it will be a loss of delta epsilon. Very quickly, I'm going to say that since those tubes, they are pointing in direction theta, and in the projection that we care about, the theta is the set of theta that is on a non-degenerate curve. So we should think that our the support is supported on some curved collection of those outside of tubes. And that's where the curvature comes in. Right? So now we are talking about gamma has curvature. Lambda has curvature. So in general, if M equals to is in Rn is like a manifold, and so those manifolds are really simple. It can be like a cone or sphere or paraboloid, and we decompose it into into a disjoint union of taus. For example, in this picture, the taus are like those outside of the tube. The decoupling asks if we have function G with Fourier transform G tau with Fourier transform supported on curve. And then G equals to sum over G tau. The decoupling inequality asks for what P and Q such that LP number of G is bounded by, there might be some loss. We call this decoupling constant and times sum over G tau. So usually usually the Q will be P or 2. And we care about when this loss is like very small. So already here you can see something that looks very similar to that. It's just we replace the 2 by Q, this 2 by Q, and this 2 by P and this 2 by Q. And it explores the cancellation because of curvature. And so usually if we use this inequality instead of that, when the curvature happens, it gives us some improvement. And that's the main idea behind the proof of the theorem. The kind of question one asks is, let's say Q equals to 2 for what range of P such that the coupling constant is bounded by, so up to some epsilon power is bounded by a constant. One thing is when M is flat. For example, in our enemy example for projections, so when this corresponds to lambda is on this square circle, then P equals to 2 is the best possible. And so this decoupling inequality, those questions was asked by Tom Wolfe, and then there was maybe as like breakthrough by Orponen and Demeter, where they proved for M to be a paraboloid and calm. And later there is work of Orponen Demeter book, where they proved for M equals to this moment curve. Already, I suppose you can see the connection between decoupling for this curve and the restricted projection that we study, that we care about at the beginning. So this is the decoupling inequality that we used in the proof. But there's one thing that here is like a union of those tubes, and so there's one step that reduces the decoupling inequality for those curve to a decoupling inequality for cone over curve, and this step is standard. It's called a Pramannik-Ziegler argument. So once we get a decoupling inequality, then we can plug in that. And so some people, maybe you care about covering the set, not by slab, but by things this shape, plank. And this is also in some middle step of the decoupling. I don't think I have time to discuss more, but that's the main idea. Thank you.
Other questions?
Yeah. So the sort of non-degeneracy condition that you've imposed on this curve
is about the determinants. Is there any the determinant of the derivatives to that matrix that you get? Is there any feeling for whether that condition is necessary for such a theorem to hold?
Yes. So if that condition doesn't hold, that means the curve is flat in some way, and then you can cook up some example.
So it's necessary and sufficient to have a Marstrand type theorem for projections like the one you had here on the board.
If you are considering like smooth curves, yes, it's necessary and sufficient. But if you consider other shapes, say not curves, but some fractal sets, then I don't know.
Then yeah.
Have you considered the case of higher K?
Yes, we proved for higher K, and for higher K it's more complicated. So yeah, the result, I erase it. The result is for all K.
Would the decoupling work in the same way?
It's more central. So in that case, the Fourier transform is not supported on the tubes, but they supported on some high dimensional shapes, and they have a lot of overlap. And we need to decompose those overlap. This region according to how much they overlap, and then we don't really have control of the shapes that come out, and we have to study what the decoupling inequality for the shapes that come out. We have to put them together. It's more subtle, and it took us a while to figure it out.
Do you get any information on the set of bad theta in your, so, do you have a correct Hausdorff dimension for almost all, but apart from the fact that it has measure 0, can you say anything about the exceptional set?
Yeah. So if you look at this thing, here I said that we proved the Marstrand inequality, but in reality we proved some kind of exceptional set estimate, like Orponen's exceptional set estimate. So, for example, in R2, if we went from R2 to R, it says that it recovers Sparkler's theorem. I don't know. Do you know?
I don't know. I was gonna it would take too long to explain it.
No, so you just plug in. So here you have your, let's say the bad set has a certain dimension, and this T will correspond to the projection image has dimension delta minus F, and then you multiply by the dimension of the exceptional set, say delta minus alpha, and then this is also the dimension of the, so you plug in and then figure it out.
So what does the broad statement say? That does it give you a bound on the Hausdorff dimension of the exceptional set, or
yes,
basically and it's some number that comes out of the other numbers?
Yeah, it's some numbers that come out of this.
I see, and that's sort of the most you can have to say. There's no nice structure.
The structure of the exceptional set.
Right.
No, I don't know. And also, so for example, in R, when you do the projection from R2 to R, there are two types of exceptional set estimate. One is the Orponen's type. And so that's when the set has large dimension, the E has large dimension, and the other type is called Kaufman's projection theorem. And our methods, I don't think it says anything about Kaufman's projection theorem.
Yeah, so is an intermediate result here some sort of Semeridi-Trotter type inequality for this incidence set? So you've lined up to give a nice inequality here, an upper bound on this IET, the measure of this set of incidences.
Yeah.
It looks a lot like Semeridi-Trotter, except you've got kind of this delta thickened everywhere.
So I think so indeed, we use this method to prove a Semeridi-Trotter-like theorem in R2, where we impose some spacing condition between the tubes.
Okay.
But just this method, I don't think you will get exactly the same as the managed controller, but because it's too strong, and there will be some common example to it.
So in 2 dimensions, though, for a collection of balls, delta balls, and I guess delta tubes or something like this, you have a semi-radiated trotter type statement that comes out.
Yes, but
Or that you can
only
show.
if the tubes are well spaced.
Right. Okay. Interesting. Thanks.
No more questions? Thank you again.
Thank you, Joanna. Thank you, the organizers, for organizing this very nice conference. So I want to tell you about some recent joint work with Brian Akra, Donald Robertson, and Florian Richter, who's right there. Florian will give the next talk by an astonishing coincidence. And so he will talk about a similar topic, but a different problem that we addressed in this topic. And so the overarching question in this project is what kind of infinite configurations do we find in sets with positive density? And so this is a question in Ramsey theory that we address using ergodic theory. So I want to tell you a bit of the story of the problem and then how ergodic theory comes in and helps us study this kind of questions. So I'll start with one of the fan favorite theorems in Ramsey theory due to van der Waerden.